Today's video is going to look at yet another way that we can use the mole to convert now to volume. So we're going to look at mole-volume relationships. And Avogadro also had a hypothesis about this as well. He said that equal volumes of gases at the same temperature and pressure are going to contain equal number of particles. Alright? And so we have to have this same temperature and pressure. So we have a standard, we call it STP, standard temperature and pressure. And this is 1 mole, which is our 6.02 times 10 to the third particles, would occupy 22.4 liters. That would be the volume that 1 mole, which is also that number of particles, would occupy. Now, the standard temperature and pressure has to have, the gases have to have the same temperature and the same pressure, and we are going to be using 0 degrees Celsius is our standard temperature. That's 273 Kelvin, 0 Celsius. And our pressure is at 1 ATM stands for atmospheres. That's just one way that we can distinguish pressure. Also, this unit, this kPa, that stands for kilopascals. So 101.3 kilopascals or 1 atmosphere. That's the pressure that's standard, and our temperature is 0 degrees Celsius. Guarantee that that is a test question, and you need to know what the standard temperature and pressures are. So let's do an example of how we can use this to figure out volume or to figure out moles. We are going to be doing some more converting. Alright? Now we want to determine the volume, so we're going to be doing liters in this case, and we know that we have 0.60 moles of sulfur dioxide, and we are at STP. That's really important. If we're not at STP, then that 22.4 liters per mole ratio does not work. So that's an important key feature right there at STP. So we always start with what we're given. We have that we're given that we have 0.60 moles of our sulfur dioxide, and we want to convert that to a volume. And that is going to be using our new conversion on the previous screen. That 1 mole of any gas is equal to 22.4 liters if we're at STP, which we are. So in this case, we're going to be able to cross out our moles and get what our liters of SO2, what the volume that is filling up. If you were to multiply those numbers together, you're going to get 13.44, and we're not allowed to record that number that has too many significant digits. We're allowed just the 2. That's the lowest amount that we have. So we can keep the 1 and the 3. We want to use the 4 there for rounding, so it's just going to be 13 liters is the volume that 0.6 moles of sulfur dioxide gas would take up. Now this one is going to be yours to work out. It's very similar to the previous problem. You have, in this case, moles of carbon dioxide. You have 3.20 times 10 to the negative third moles, and we are at STP, so we can convert our moles to liters. Is asking for a volume, so liters would be sufficient, and you want to make sure that you're recording your answer with the correct number of significant digits. So you're going to be working on that one, and I look forward to seeing what you come up with. If you have any questions, please let me know. And let's move on to another problem. We are at STP, again that's important, and we're given the density. The density of our gas is 1.964 grams per liter. Remember that density is mass over volume, so we have a mass and a volume. And we want to know what the molar mass is. And we can calculate the molar mass if we knew what our gas compound was, but they don't tell us a formula. So we want to be able to calculate a molar mass given this information. Now remember that a molar mass is the amount of grams per mole of a compound or an atom, whatever we have. And so if we look at what we're starting out with, we're starting out with 1.964, and that's grams per liter. So we already have the grams unit that we want here at the end. What we want to get rid of is the liters. Liters needs to go away because we need to convert that to moles. That way we can have a molar mass. Now this is just like any other problem. What you want to get rid of, in this case the liters is what we want to get rid of, needs to go on the opposite side of our division bar. So we are going to put liters on the top. That way liters will cancel. And we want to put, what we want needs to go in this case on the bottom because we want moles. And we have a conversion now from liters to moles with our new conversion factor that says 22.4 liters is equal to a mole. And so we can multiply our two numbers together, and that will give us grams per mole, which is a molar mass. And if we do that, we're going to have 43.9936. Again, we need to look at significant digits every time. We have 4 significant digits in our first problem. 22.4 liters per mole is a standard. It's an absolute value. So we are not going to be using that for significant digit purposes. So we're allowed to keep 4 digits. And if we take a look at those first 4 and then our next one for rounding, you are going to be left with 43.99. And again, that's the grams per mole. One more problem to work out together, and that is that we want to calculate the density of krypton gas at STP, so standard temperature and pressure. Density, remember, is mass over volume, so it could be grams over liters, grams over milliliters, but we need to have a mass and we need to have a volume. Now if we were to, and they give us no number to start off with, so we're going to have to use our head here for a second. What do we know about krypton? You know the molar mass of krypton by looking at a periodic table. 83.8 if you just look at the periodic table, and that is grams per mole. Keep in mind molar mass, grams per mole. So we already have the grams just by the molar mass, and what we want to get rid of now is the mole. So mole in this case goes on top, and we can convert to liters with our new conversion, 22.4 liters per mole. Liters doesn't go away. We don't want that to go away. We want moles to go away. We want liters. We want grams. Sorry about that. When we divide these, we are going to get 3 point and several numbers. Again, significant digit wise, we are allowed 3. 83.8 has 3 in it. And so 3.74, the 1 is not going to affect our answer. So 3.74 grams per liter. And that would be a density. We have mass over volume. The mole is kind of the roadmap to everything that you need to get to. I want you to notice that moles is right in the center. So if you need to get to a representative particle, you're going to have to go to a mole. If you want to get to the mass of something, you're going to have to go from wherever you're at with particles to moles before you can get to mass. Moles is going to be something that we use a lot in chemistry just because it is the center of all these. If we have a mass and we want a volume, we need to convert it to moles first, and then from moles we can go to our volume of liters. So the mole is kind of the center of all of your chemical equations. It's definitely not something that's going to go away anytime soon. We're going to be using it the whole rest of the trimester. And yeah, the mole's the intermediate step. So whenever you want to get from particles to mass, it's going to be a 2-step problem. You need to go to moles first and then go to mass. We've practiced with those. We're going to be practicing giving the mass of something and you converting it to liters, kind of what we started today. We are also going to be able to convert liters over to molecules and atoms and things like that. So mole, very important. We've learned 3 conversions so far. We've learned the grams to moles with our molar mass. We have our moles to molecules with our 6.02 times 10 to the 23rd. And now we have a mole to volume conversion with our 22.4 liters per mole. And all of those we will be using frequently.